Alrighty, part 3 of integration by parts. Let's go ahead and jump in with a definite integral. Let's go ahead and do 0 to pi over 4 x squared sine of 2x dx. And just for the sake of showing you the tabular method again, even though it's only x squared and it would require 2, let's just go ahead and do it by the tabular method so that we see it again before we're all through with these videos. And so we have x squared, which becomes 2x, which becomes 2, and after 3 derivatives, it disappears into 0, okay? Sine 2x, when I anti-differentiate, becomes negative cosine with the appropriate coefficient out in front, which becomes sine 2x with the appropriate coefficient out in front. And then, of course, it turns back positive the moment that you anti-differentiate sine again. So we have 3 terms go over and down, over and down, over and down. Okay, which means I have x squared, negative x squared over 2 cosine 2x plus x over 2 sine 2x, and then plus 1/4 cosine 2x. Well, if you're going from 0 to pi over 4, that actually shouldn't be too overly difficult to actually plug in. Winds up being kind of a pain, but you could actually do it. Let's go ahead and just see what the let's go ahead and see what it looks like in terms of on the calculator. Okay. Because I don't want to waste our time on a bunch of algebra. But let's go ahead, see, we have it in y1, and so if I want to integrate it from 0 to pi divided by 4 y1 dx, and you have 0.143, okay? The interesting thing is that when you actually plug in the 0, right, the only term that's actually going to survive is going to be this one right here, which is going to wind up being 1/4, okay? When you plug in the pi over 4, cosine is going to be cosine of pi over 2, which is 0. So in both of those, something is going to disappear. Actually, let's go ahead and do it. So we know that when we plug in pi over 4, you're going to get negative pi over 4 squared over 2 cosine of pi over 2 plus pi over 4 over 2 sine of pi over 2 plus 1/4 cosine of pi over 2. That is plugging in the pi over 4. You go ahead and plug in the 0, and you're going to get negative 0 squared over 2 cosine of 0 plus 0 over 2 sine of 0 plus 1/4 cosine of 0. Well, that term goes away, that term goes away, that term goes away, that term goes away. And the only thing you're really left with is, and of course this right here is equal to 1, you have pi over 8 minus 1/4. Okay, now is pi over 8 minus 1/4 equal to what we got on our calculator? Well, let's go ahead and see. Let's see if we can turn the light, see if that makes things better. And we have pi over 8 minus, and we'll go ahead and put 0.25 for that. Oh my gosh, will you look at that. Okay, so score. Oh, we got the right answer. Let's go ahead and do another one. Okay. Let's go from 0 to 1. of x times arctan x dx. Okay? Now, we should try and remember occasionally what some of these look like so that we know whether the answer is reasonable. Now, we should expect for this answer to be less than 1/2. Okay? And here's why. Let's go ahead and look at the graph. That graph, that straight line right there, is y is equal to x. Okay? This curve is arctan x. We are being asked to look at the product function of those two, okay, from 0 to 1. So let's go ahead and include the product function. That's that curve right there. Okay, so the product function, let's actually go ahead and just look at it. You notice that if I were to just ask what the area is of y is equal to x from 0 to 1, you could use geometry, right? It's just this triangle right here. It's half of the box. It's half of a square with side equal to 1. So it'd be 1/2. And I know from my knowledge of arctan x that arctan x kind of sweeps out underneath that and only reaches 1 right about here, okay? And if I'm going to actually take the product of those two, I know that that product function is going to be under both of those until at least it gets to 1, at which point it's equal to arctan of x. And so I know from my knowledge of product functions and graphs that it's going to be underneath y is equal to x from 0 to 1, then I know that its area from 0 to 1 is going to be less than that 1/2 that I just sort of reasoned out using geometry. Okay? Now, that's what the graph looks like. Kind of neat. And we should have expected it to kind of look like that. Let's go ahead and zoom out just a little bit. We should recognize the fact that this is an even function. It's an even function because x is odd, arctan x is odd, and the product of odd times odd is of course even, because a negative times a negative is a positive. Now let's go ahead and look back here. Now, I know that what I would really like to do is I would really like to make x my u. But I know that that's probably not a good idea. This is kind of the exception to the rule, because I can't anti-differentiate arctan, okay, at least not easily. So I'm going to make my u equal to arctan x, and I'm going to make my dv equal to x dx. Now that means my v is 1/2 x squared, and my du is going to be 1 over 1 plus x squared. Let's actually turn that into a dx so we can save space, basically. So I know, and let's go ahead and just work on it in terms of it being a indefinite integral just really quickly. We get 1/2 x squared arctan x minus 1/2 x squared over 1 plus x squared dx. Now, that winds up being arctan x minus 1/2. Now, there are several ways that you can go with this. I would go ahead and take that numerator and add 1 and subtract 1. Using the additive inverse, which basically is going to give me 1 minus 1 over 1 plus x squared dx. If I go ahead and do that, that winds up being arctan x minus 1/2 integral dx plus 1/2 integral dx over 1 plus x squared. Well, that shouldn't be too tough. Arctan x minus 1/2 x plus 1/2 arctan x, and I need to evaluate it from 0 to 1. Well, I don't really have to worry about evaluating it at 0. I know that both arctan x and x are both 0 at 0, so really all I have to do is evaluate it at 1. Well, that means 1 minus 1/2 times 1 minus 1/2 times arctan of 1. Okay? And I'm just going to ignore the second part of it because I know it's all going to work out to be 0. What is arctan of 1? Well, you should remember that that's pi over 4. Okay? So this winds up being pi over 8 minus 1/2 minus, did I mess up somewhere? I think I may have. Um, Oh, yeah, because it's plus here. Plus, okay. Yeah, that's where I messed up. Pi over 8. And so you're going to wind up getting pi over 4 minus 1/2. Okay? Now, let's go ahead and see what that looks like if we were to actually do it with the calculator. First of all, let's evaluate pi over 4 minus 1/2. And then, and I'm just a sucker for doing this, so let's go ahead and plop that into y1. Okay. 0 to 1, y1 in terms of x, and there we go. Okay, it's exactly the same thing that the calculator algorithm figured out. So what we need to do is we need to be able to do it by hand. A lot of these on the AP exam are going to, there are a lot of integrals on the AP exam when you finally get there that actually just ask you to set the problem up. Or it's on the calculator section. And so being able to do a whole lot of integration by hand is useful, but it may not be it's not going to be, it is going to be very, very useful, but a lot of the stuff on the AP exam just asks you to set up the integral, or it asks you on the calculator section. But you still do need to have your integration skills sharp as you move forward. So please do, every once in a while, go ahead and work it out by hand, making sure that you remember actually how to do that. Let's go ahead and do that one. Okay, now, what does that function look like? Well, I happen to know that this function is the product, of course, of the radical function and the natural log function. Okay, I know that this doesn't actually become greater than 1 until it reaches e, which is about 2.78. So on the interval from 1 to 2, this actually at 1 starts out at 0 and doesn't quite get up to 1. So when you're multiplying by natural log x, or the area under natural log x, you're going to be pulling that radical function down. Okay? And so if we have, and let's go ahead and look at that. It's always a good exercise to go ahead and look at the graph. So you have that, and then let's go natural log x, and then let's go ahead and do the product function. Actually, let's go ahead and stop. Let's go back to the window. Let's go 0 to 3, which includes our window, and let's go 0. Let's go -1 to 2, which also includes our window. There's the radical function. Here comes the natural log function. Here comes the product function. Okay, so we see that from 1 to 2, which is this interval right here, it's going to be greater than the red function, which is the natural log function, but less than the radical function. But it's still going to give us quite a small area if this integral is actually set up for area. Remember, the integral is not area, but we can always sort of make sense out of our answer if we relate it to area, if we understand the shape of the graph of whatever function is in that integrand. Now, here again, we want to go ahead and put natural log x as my u, because you're not going to be anti-differentiating natural log x. The only real thing that you can do with that is actually to differentiate it. So if we have x to the 1/2 dx as our dv, we know that that's going to be 2/3 x to the 3/2. So 2/3 x to the 3/2 natural log x minus, well, that's going to be 2/3 x to the 1/2 dx once the x to the 3/2 gets cut by that x in the denominator. And therefore this winds up being a very easy integral, so 1 to 2 still. And so we have 2/3 x to the 3/2 natural log x minus 4/9 x to the 3/2 from 1 to 2. Now this you can actually go ahead and factor out. If that actually helps you. Sometimes in factored form it's a little bit easier to do the arithmetic. But it's still going to be a calculator problem even after you've done this by hand, largely because you can't take the 3/2 power of 2 without getting an irrational number. You can't take the natural log of 2 without getting an irrational number. But I mean, doing actually the integration right here and getting it down to here is helpful. So let's go ahead and do it. Remember that we plugged the product function into y3. So let's go ahead and go back to the main screen and let's integrate it from 1 to 2. So we integrate it from 1 to 2 of y3 dx, and it winds up being about 1/2. Okay. Now we could, if we wanted to, go here and actually plug in the integral, okay, from 1 to x of y3 dx, which actually makes y4 a function, okay? I don't want to actually see it, okay? So let's go ahead and turn it off in case we do go back to the graph. Now all I have to do is evaluate y4 at 2 in order to get my answer, okay? And so if I go ahead and evaluate y4 at 2, and there we go, it's the same thing. You could go ahead and say, well, what is 2/3 times 2 to the 1.5 times natural log of 2 minus 2/3. And then of course you can do the same thing with 1. Let's go ahead. So I'm just, you could actually, work this out a little bit. 1.5 natural log 1 minus 2/3. But I mean, either way, this is a calculator problem. So that minus that, and we get roughly the same thing that we got above. It's only different in the very last decimal place. This one was just a calculator problem. Either way you went at it, whether you went at it from the beginning or whether you actually integrated it by hand. Obviously the integration by hand is helpful to always sort of keep our skills sharp, but some of them are just, they're just calculator problems. That sort of brings us to an end of our discussion of integration by parts, I think. I'll go ahead and move on to the next section. However, if any questions remain unresolved, please do email me and I will try to resolve them. I look forward to hearing from you, and if not, I look forward to seeing you on our next Skype session. Bye.